Okay, continuing with logarithms, let's look at branches and derivatives of logarithms. Section 331. Okay, I'm going to try to make some resolution out of this many-valued versus single-valued deal with multiple valued lowercase l log z versus the single valued capital L log z function. This one's really a function. Lowercase l is a set valued function, or it's got some problems. And this section resolves that to some degree. Note 3.31a says that alpha denote any real number. Any real number. It's going to act as an argument. That's the reason that they've chosen a Greek letter. For any complex number z, such that z equals re to the I theta, by convention, we only take r values to be positive in polar representations, and any theta between alpha and alpha plus 2 pi. So theta ranges over an interval of length 2 pi, centered at alpha. I'm sorry, beginning at alpha. Under those conditions, define the log of z to be the log of e of re to the I theta to be the natural log of r plus I theta. So here's yet another definition of log. Now the benefit of this one is it's actually a function. You put a complex number in and you get a single complex number out. We had no problems with the real part before. It was always the natural log of the modulus, which is what it is here. It was in the choice of the argument. Here we've chosen to pick an argument which lies inside this particular interval. So unfortunately, this is the same notation from the previous section, but in the previous section we had a multiple valued function. Now we've got a function. A particular function, this is what will be called a branch of the logarithm. Polar coordinates, it's easy to pick off the real and imaginary parts. They are just simply the log of r and theta itself. These are defined not everywhere. So you'll notice this is an open interval. So this is defined, this log function is defined for all complex numbers except those with an argument of alpha. Anything bigger than alpha, up to alpha plus 2 pi, we're good. But alpha is not included, nor is anything coterminal with alpha included as a possible argument. So this is defined for the complex plane except set minus. Complex numbers of the form rho e to the I alpha, where rho is greater than or equal to 1. Greater than or equal to 0. Of course, we're not going to take a log of 0. So that's where the rho equals 0 part comes from. But I stepped aside and made a little picture. So what we're doing is taking the whole complex plane and we're going through an angle alpha and looking at a line. All the points along this line have an argument of alpha. In the picture, it's a principal argument, but that's not necessarily relevant. And we're excluding the origin because we're dealing with a log function. And what we're doing is taking the complex plane, kind of like taking scissors and cutting from 0 along this straight line. And these are the points that are being removed. It'll be called a branch cut shortly. So these points are being peeled out of the complex plane, and we're defining a branch of the logarithm on what remains. Returning to the notes. Domain is as drawn in that picture. So we've got a log function defined. It will satisfy the Cauchy-Riemann equations. We got the real and imaginary parts, so that's easy to confirm right there. Then we know that we're dealing with an analytic function. The Cauchy-Riemann equations are satisfied. The first partials, these are 1 and 0, so those are continuous everywhere. Everywhere they're defined. So this function is analytic where it's defined. It's defined on the set D, That's what the symbol D indicated. So we can differentiate it. Take a derivative using the partials of the real and imaginary parts, as we would, I guess, section 23, 2.23 deals with expressing derivatives when we've presented something in terms of polar coordinates. But we get, for the derivative, no surprise, we get 1 over z. So we have a function, a single valued function, if you will, that will, because of the form of it, guaranteed to be a candidate for an inverse of the exponential function where it's defined. And it has as its derivative 1 over z. So things are starting to fall into place. This sounds like your old chum, the natural log function from the real setting. It's an inverse of the exponential function, and it has as its derivative of log z is 1 over z. So quite similar to the natural log function from complex numbers, at least in the sense of being an inverse of an exponential, and its form of differentiate, it's the form of its derivative. A special case of this approach is to take the principal branch of the logarithm. We'll take alpha to equal negative pi. Up here where we had chosen alpha, here it is, chosen theta to be between alpha and alpha plus 2 pi. If we'll take alpha to be negative pi, then we're choosing angles between negative pi and positive pi, excluding the endpoints. Then the angle that's being chosen would be the principal argument. And that leads us to the principal branch of the logarithm. And this is the same function we encountered in the previous section. And its derivative, as shown here, is 1 over z. And it's defined except at alpha equals negative pi, or anything coterminal with that. So the principal branch of the logarithm, the way this book chooses to choose principal values, is not defined on the negative real axis. So we've gone to alpha equals negative pi. That'll take you to along the negative real axis. And just as we had in the picture, alpha equals negative pi would give us the negative real axis along here. So the cut's been made along this axis. We lose 0. Of course, we lose 0 because we're talking a log function. And we lose all the negative real numbers, which is a little messed up because that was one of the cute things about complex numbers, is you could take logs of negatives. Well, you can still take logs of negative real numbers. You just can't use this branch of the logarithm to do it. You'll have to use a different branch of the logarithm. All right, and a bit of notation. Yes, these are called branches of the logarithm. The set, where we've taken the complex plane and cut out a little piece, is called a branch cut. The point z equals 0 is called the branch point. And we've now introduced branches of the logarithms. They're all based on choosing arguments in some standard set. You change alpha, you change the branch of the logarithm, but it comes with a branch cut. So when you choose a branch of the logarithm, there's going to be a set of complex numbers other than just 0 where that branch of the logarithm isn't defined. You might think to yourself, why don't they just include that right-hand endpoint? Well, they got their reasons, and their reasons are related to continuity. If you include that right-hand endpoint, you're going to produce a function that will behave on the interior just fine, but you're going to have a continuity issue at the endpoints. And what happens is, if I look at points near the branch cut on this side, they have a certain argument. And if I go around and look at points near the branch cut on the other side, they have an argument that differs from points over here by roughly 2 pi radians. So you're losing continuity in terms of a log function. So that's the reason that they don't include the branch cut, the part that's been pulled away. It's to keep these functions, these branches of the logarithms, to keep them continuous on their domains. And That's how we'll approach logarithms. Probably most commonly, we'll use the principal branch of the logarithm, but not exclusively. We could pick any one, and you've got to tell me which one we're going to pick before we start with computations, because the argument thing is an issue. But it gives us different branches of the logarithms. Now, these ideas will carry over to other multiple valued functions in this chapter. And the other multiple valued functions are square root functions and cube root functions and fourth root functions. So as I mentioned at the end of the previous section, we've calculated square roots, but we haven't had a square root function. We calculated cube roots, but we didn't have a cube root function. We're going to need branches of a square root function. We're going to need branches of a cube root function, because if I'm taking cube roots, there's going to be 3 choices for cube roots for each input value. We need a protocol by which we choose exactly one of those so we can create a cube root function. But there's going to be 3 choices. So we'll have 3 natural branches of the cube root function. With a square root function, there'll be 2 choices. So there'll be 2 branches of a square root function, 2 natural choices for branches of the square root function. And that's why when you take square roots, do you take the positive square root or the negative square root in the real setting? You take the non-negative one because that's what the square root symbol means. Well, we could just as easily said, well, no, the square root symbol means take the negative square root. Don't do that because nobody else does it. But that would be an alternative approach to defining a function, which is, as its inverse, the squaring function. So you haven't seen the last of this branch cut stuff. And as I've commented multiple times, the whole reason we're having multiple branches is because of the polar coordinates and because of the behaviors of arguments. Okay, bye-bye.